Let me introduce Heino. Heino got his PhD at Max Planck Institute for Radio Astronomy in Bonn a good deal later than we got ours, sadly.
But that's true for 99.8%
for the rest of the world, right? He did a postdoc there and then went to the University of Maryland and went back to Bonn, worked on VLBI. Was project scientist for Astron in Trianon, and is now professor of radio astronomy at Nijmegen?
Yeah, perfect.
Is that okay?
Great.
University.
Yes.
And I've just been learning from him how LOFAR, which he's going to talk to us about, manages to get their operating funds. It's something about which I'm very sensitive right now. So thanks, Heino, for joining us, and I'm really eager to hear all about LOFAR, but it's particularly the SETI bits at the end.
Yeah. I have to apologize right away. That's probably one of the worst talks I've ever given, because things have been. We had been up to a slow start in LOFAR, but now things keep pouring in. So the first commissioning results, and so I couldn't really concentrate on just one aspect. So what I'll try to do is I'll give you a little overview of what LOFAR is, in case you haven't heard it yet. Then I'll show some commissioning results, hopefully to impress you, to show that things are going well. And they're going well, but it's a lot of hard work. So and then I'll talk a little bit about the stuff we are doing that is, I think a bit of innovative way of doing radio astronomy at very high time resolution, very flexible, using phased array technology and buffer boards. And that's something I thought we could also use for SETI type research. And the idea is actually I'll just present some of the ideas I have, and then you later tell me it's all crap, or we'll just get to some discussion whether that should be done or it's useful or not. So LOFAR is actually it's an SKA pathfinder, even though SKA is not a very popular word in the US. So I had just lots of discussion with Sri Kulkarni about it, but I still think SKA is a great thing to do. And LOFAR is, I think, one of the first stepping stones towards this. It was built around 4 key science projects. One is the epoch of reionization. That is, getting the H1 hydrogen at a redshift of 10. So that's when the first stars were reionizing the universe. And that is one of the most challenging projects of LOFAR indeed. Second one is just surveys, because LOFAR has a very large field of view and at low frequencies. So we haven't done a large sky survey in a long time. 3C, of course, was out there, and then there are not too many surveys out there, and essentially we have a sensitivity to see all radio galaxies out to redshift of 100 if they are there, right? So that's of course we don't know it's redshift of 100, but in principle we see really a complete inventory of for example, active black holes. Then one thing that we are heavily involved in is high-energy cosmic rays, the direct detection of cosmic rays, and then the second thing that is closely related is transients and pulsar detections. And so it's something I want to spend a little more time on these two aspects. Now, of course, right, so, the good old Westerbork telescope. And if you want to...
that's Shostak.
And unfortunately, this is a time-lapse movie, so it doesn't really move that fast. But that's how you do, normally in radio astronomy. You point your telescope in certain directions, and you only see what's coming from that direction where you're pointing to. LOFAR is quite different. Consisting of about 2,000 of these low-band antennas, essentially pieces of wire with an amplifier up here. There's an electronic cabinet in the back. There's AD converters, beamformers, and then you send it off to a central computer in Groningen where you do the correlation between different stations.
Is there any ground screen anywhere?
Sorry?
Is there any ground screen?
There is ground screen, yes. You may see it later if I have another picture. Well, okay, just give you the... there's a ground screen. So the basic idea, most of you really know, but maybe one or two who don't. Dish usually receives a plane wave, focuses it, and then you have one receiver in the cabin. And if you're really good, you may have a focal plane array, then you actually have multiple directions. But essentially, that's what focuses your your wave into one location. Now, what we do is we replace the dish by actually lots of receivers. The point is that steel is very expensive, receivers get cheaper and cheaper. They're essentially, a lot of what's happening here is silicon, which also gets cheaper and cheaper. And so you replace it by a plain array of receivers, and then of course the wave will not arrive in phase, it will actually arrive at different times, but you can actually digitize the wave at each point, because we have radio waves, and you have quantum occupation numbers which are gazillions. If you calculate at a low frequency, these are perfectly classic objects. So you can digitize the entire wave in your computer. You can store it, you can reprocess it as often as you like. And so what you then do is you sort of take out the time delay, for example, away from this direction, and then add things in phase. Essentially, do a ray tracing, do a ray tracing of that dish here in your computer. And since you have a digital array, you can do the same. It doesn't matter whether you look in this direction or this direction. And in fact, you can look in both directions at once, because you can reuse the same data over and over again. And that's the beauty of the flexibility of this telescope. It also means you can switch as fast as you can switch your computer, which is amazingly slow actually sometimes. It takes a second or so to switch the entire system at the moment. So, but that means you can do all sky, larger field of view, and other things. In addition to that, we have a new feature which I think no other telescope has at the moment, and that is these transient buffer boards, which is sort of half a gigabyte of RAM for a couple of antennas. I think half a gigabyte of RAM per antenna, plus an FPGA to do some processing. And so the raw data that comes from the antenna, which actually will be piped through a ring buffer, which at the moment stores 1.3 seconds of data, full bandwidth, so everything. So for 1.3 seconds, you have the entire sky in your, that's shown here, the entire sky in your field of view in each of those buffer boards. And you can actually download this later and then reprocess the data and then do what I just showed and look in all directions at once. Of course, you have to know something interesting had happened, because after 1.3 seconds, the data will be gone. There are some tricks you can play, which we have not yet used so far. You can only store a fraction of the bandwidth and thereby extend the buffering time to 30 seconds or so, but then you only use a fraction of the bandwidth, not all frequencies. And I'm actually going to expand this to 5 seconds in the near future. So,
and the expansion is just RAM?
It's just RAM. In fact, you can go to 10 seconds. I mean, I probably will just spend money for 5 seconds, but if someone else wants to spend another 300,000, it's just 300,000 euros, and you get to 10 seconds extra. So that'd be quite interesting. Yeah, and then you have all frequencies, all sky for 1 second, or 5 seconds, or 10 seconds. That's of course quite potentially interesting to do things. Now, what I'm interested in is really short time scales. I mean, the idea is that something flares up there in the sky, you dump the buffer, and then you later find out where it came from. And there are a few known things that we know about. One thing that we actually sort of pioneered recently was these ultra-high energy cosmic rays. Why didn't that work? Let's see. Anyway. That was supposed to be a cosmic ray coming down. There it is. All right. So a cosmic ray hits the atmosphere, produces a shower of particles, and makes a radio flash, actually, with sort of gigajansky radio flares in about 20 nanoseconds. The other things that you know about are solar planetary flares, which have millisecond time scales. And in fact, we know that this is also true for things like brown dwarfs and some nearby flare stars. M dwarfs make these radio flares. And there's people speculating about exoplanets as well. But the question is whether they get as bright as you need to. The other short timescale things are pulsars. This is the animation of a pulsar. You have to look like this, right? So there are two ways of looking at this. It's an optical switch you can make in your mind. Some people understand what I'm talking about, others not. So that's a pulsar, and actually these can have giant pulses down to nanosecond timescales. So suddenly you have a flare of a nanosecond only. So it's quite amazing. You have 30 seconds, sort of something which is 30 light, one light foot essentially in length. You can see out to several hundreds of light years. Or other things like lightning. In fact, what you see on the right side here is this one here. All right, and of course the third one. This one just too quickly. That was a joke. Okay, that was a little green man that you also may be able to see, if it's only very transient. And that doesn't really connect well, so I have to put it this way. So, LoFar is not just those low-band antennas, it's also high-band antennas, so low frequencies 10 to 80 megahertz, and high frequencies 120 to roughly 270 megahertz. And then at high frequencies, you actually have these tiles. These are actually 16 cross dipoles. These are bow tie antennas, which are sort of stabilized in this styrofoam structure. Actually, so if all the Netherlands, due to global warming, will go underwater, LoFar will still float. So that's a good message, actually. In fact, we actually also added, from our group, 20 particle detectors in the center of LoFar to detect cosmic rays. So we have this interaction. So LoFar truly is the sensor network. And so that is now...
But you only have the transient buffer boards on the low-band antennas.
We have them, not on every antenna. So they share the same digital electronics. So they both have buffer boards. So whatever you observe, you can only observe one at once. So there's one receiver for two elements, so you have to choose between the two. You could have subarrays and whatever. You can be very flexible. But they both have buffer boards, yes. So there's one station, it's hard to see. This is, of course, these are the tiles. So we call this the Mickey Mouse. These are the ears of the Mickey Mouse, and here in the center is actually a big circle, which is hard to see, of the low-band antennas. And if you see very carefully, there's sort of squares here. And this is a ground screen, which is just a wire mesh on the ground. That's one station that we use, and this is the central core, the super TARP. Now, some of you who've been in Groningen will know that TARP actually is not what I used to know it from Maryland, the super TARP here, but is actually a hill that the Dutch used to defend themselves, and let the Romans sink into the mud in the central area. In fact, when we built this thing, some of our equipment actually sunk into the swamp there, which was in winter, and in fall it gets very muddy. Anyway, so there are 6 stations here with these high-band antenna tiles and the low-band ones. And then you go further out. All these green dots are locations of stations. 27. There are going to be 40 stations in the end. 27 are finished at this moment. And a couple more have been built or are in the process of being built. There are sort of a handful which is still a bit more uncertain. But that's a fairly large array. But we're not only having these stations, we also have stations throughout Europe. This is an international station. We have the International LoFar Telescope. That's ILT, that's what this stands for. They are actually twice as big in terms of collecting area, the international stations. And they are distributed over, we have one in England, there's one in France, it's a Marseille array. There are 5 in Germany at the moment, there will be a 6th one in Germany, it's one in Sweden that's being under construction right now. And actually 1/3 of the collecting area of LoFar is actually in international waters, I almost said, throughout the rest of Europe. And that gives you quite large baselines, up to 1,000-kilometer baselines. And we hope to actually get some stations in Poland as well. So it looks reasonably positive there. There are up to 3 stations in LoFar. At the center of LoFar, we have this IBM Blue Gene correlator. Actually, computer is a supercomputer. This used to be the fastest supercomputer in Europe for about 2 weeks. So the Spaniards had their ones, and they brought extra equipment in to make it even faster, just a little bit. Now it's sort of an average computer, after 2 or 3 years. Well, it's good. It's a general purpose computer, essentially. And so you can reprogram it. So you can run different kinds of programs. It's not just doing correlation. You can do other things on it as well. In fact, people have run MHD simulations in the beginning on it. So that's quite useful. In addition to that, we have an offline cluster. There's a big sort of 100 node or so offline cluster which does post-processing. So it's not just that. So the imaging and so forth is running on an offline cluster thereafter. Now, this is for radar astronomers. These are sort of phases and amplitudes of our solution. So just to show you, it's real interferometry data, and it's actually very good data. It's actually very clean data. So people have used other radio telescopes. They come away from this saying, well, this is some of the best data we've seen, actually. So in terms of data quality, that's really good. We also can do fairly well with RFI. It's not the biggest issue we have in LoFar, despite what many people have said. RFI is really not the thing we really, lie awake from.
And is that because it's a distributed array?
That is part of it, but also because the low frequency regime is not so crowded at this moment. There's airplane traffic, there's a lot, and between 30 and 80 megahertz is completely empty almost, until digital television comes, but I doubt it will go to 50 or 60 megahertz, so that's a fairly low frequency. The real challenge at low frequency is the ionosphere, and this is sort of an impressive movie, I think, that sort of Hugh Rutgering and his students made from GMRT data, where they look at sort of, this is the calibrated image, and this is sort of the non-integrated, non-calibrated image you get, and you see, the kind of seeing how the source wanders around. That's something you really have to take out and calibrate very well at these frequencies. Of course, this is GMRT in India. It has much worse an ionosphere than in the Netherlands, so it's not as bad as here. But that's where the source should have been, right? And sort of been moved out of the main beam. So that's one of the challenges we're still struggling with. And then the next one is the pointer. Is then the beam, calibration of the beam. A phased array is great, but it requires a lot of calibration. That is the beam you have on the sky. If you track the source, your beam changes. Yeah, if you have a single dish, your dish more or less stays the same. But what happened here? I don't know. Strange. So the element beam changes and the station beam changes as a function of time. And also that we have not done a good job yet at really calculating it and calibrating it out to sufficient enough quality to get the best results. Nonetheless, results are coming out. This is a sort of cutout image from a map that was made by the OR Key Science Project. This has now mini-Jansky noise at 120 megahertz. That's actually quite substantial. Dynamic range of 40,000 to 1. So one of the deepest images made with LOFAR so far. Probably it's this frequency so far. This still has a lot of artifacts here. It has not been deconvolved, so that will happen actually as we speak. So they want to make actually a press release about the image at end of the week. So, you can get some reasonably high quality image. Of course, they want to go to dynamic range of 10 to 6. And we're still factor 10 here away from the thermal noise. So not all the artifacts have been taken out. And I think that will still take a year or so until we really get to the high quality images that we need. But nonetheless, that already is quite interesting. Mini-Jansky level is, you can do something with it. But that corresponds to 100 microjanskys. You have the SEEP spectrum at gigahertz frequencies. And you have here a 2 by 2 degree field, actually larger. Actually at low frequency you have almost 5 by 5 or even 10 by 10 degrees. This here is going to lower frequencies. This work by the Survey team. The 50 megahertz. Again, sort of frequency has been laid, which was completely empty or not used in the past. With 26 stations. Only a fraction of the bandwidth so far. This is a cluster at redshift of 0.5. Which you map nicely, and you see lots of sources. I mean, every pointing you make with LOFAR is full of sources. And that's of course the idea. When you make a nice survey out of it. So it's 50 megahertz, it's 30 megahertz, 20 megahertz. I mean, it of course gets worse, and the field of view gets larger. But you can make images. So this is 100. Well, the 50 megahertz was sort of 100 millijansky levels. Was not yet at the level that you would like to get to. But anyway, I mean, it's already much better than anything else that sort of has been done at those frequencies. Better than VLA. We've been working at M87. It's not yet full resolution. It's also just a fraction of the bandwidth that we've been using so far. That's M87 is a radio galaxy when you are not a radio astronomer. So it's a supermassive black hole spewing out a plasma jet. And we see stuff, actually extending beyond what the VLA has done in the past. It's again still not perfect, but it's getting there. Then what's very nice is actually we're putting the long baselines to use. So this is actually the first image I showed was a Quasar 3C196, and then with a Dutch station, it's just completely unresolved at about sort of 11 arcsecond beam. And now Olaf Bucklitz from Bonn has used international baselines. Gets to 0.3 arcseconds, resolves the source into a double structure, which we knew from higher frequency they should be there. But definitely, this resolving power is there. And again, at these frequencies, I think, those high resolutions don't exist at all. That's completely a new capability that we have now at our hands. Again, a lot of work, so it doesn't run automatically. It's a crap nebula on the right side, and then a VLBI image on the left, which just shows the point source. Then there is one other aspect of it is a transient search. So this may be our first transient, probably is. This sort of one. Sorry, these images are all ugly, but radio astronomers tend to emphasize the noise, right? So they always like to make the most ugliest images you can make. I try to change that, but sort of they are resistant to these suggestions. So that supposedly are nice images, but sort of you have here a source, and there's one, and then that's an older image, so the source wasn't there in the past. So somehow a new source appeared somewhere between April 2010 and August 2010. And it's sort of, we don't know what it is. And that's one of the things you want to do with LOFAR, because you have a large field of view. You want to look at the sky over and over again and see sort of is there transient sources. So something like the PTF, the Pelham transient factor, and the optical, we'd like to do in the radio, and follow it up. I mean, okay, I'll say this in a very suggestion. What could these things be? It's just complete. So it's a plug for things we've just very recently done. So you may ignore it because it's not directly. It is somewhat related to LOFAR. The idea we had was, okay, let's assume we have a supermassive black hole, you have a star coming by, it's being disrupted, and then actually what happens is you have an outflow of a plasma jet. That's what we've been working on for the last couple of years. And so we've learned from stellar mass black holes and from supermassive black holes how this behaves. When you switch on a jet, what the radio emission is, and so we predicted light curves for time since disruption here in the millijansky. You get several millijansky radio flares from jets which suddenly switch on if the star gets swallowed. And so luckily, almost 2 weeks before we submitted the paper, this GRB 110328, I think, I always forget the number, was found, which created a lot of interest because this might have been the first gamma ray flare that was created by such a stellar tidal disruption, and it showed a radio flare at the same time, which was exactly, then sort of still order of magnitude, but pretty much what we predicted with this simple model. So that's one of the things that we could find with LOFAR, and actually even better so with the Allen telescope array, I should say, because that one actually do better with higher frequencies. Another one kind of transients that you want to see is, for example, supernovae. Again, a plug for a paper we had recently. Supernova 2008 IZ, which exploded 2008, obviously, but was found in 2009 just by chance. And the actually we followed it with VLBI. You actually see nicely how it expands. So it's actually beautiful supernova. But the interesting thing is, in M82, it was not seen at all at any other wavelengths. It was not seen in the infrared. It was not seen in the optical. It was not seen in any gamma ray emission. It was only seen in radio. So we may be able to find a few things that other guys don't find in the radio because it's completely absorbed, for example, by dust and so forth. And again, in principle, I would think that this would be done better at higher frequencies. Again, the Allen telescope array rather than LOFAR. But LOFAR, of course, has the advantage of large field of view things. So. Okay, so transient is one interesting aspect. Well, the sun, well, here's an image of the sun, the solar flare, sort of, which LOFAR gives you. And then what's happening?
Do you get enough resolution to see which side of the solar disk the flare is on?
Well, sure, it's over here. That's the solar disk.
Oh, okay. Got pulsar.
Sorry, yeah. Sorry, yeah. That's was too quick. Where to start? All right, so that's the solar disk here.
Okay.
And then here you have the solar flare on one side. And again, this is not full resolution. It's actually very crappy data. I mean, you can do this much better. It's not well done yet. It's just the first try. Then what you actually can do, if you have such a phased array, you can actually use it in different ways. One way is, as I said, to do the interferometry. You just cross-correlate the different stations. And what you do here for pulsar search is you phase all the stations up. So you combine them such that they act as if they were a single dish. And then you place this single dish beam onto a pulsar, for example, and want to measure its pulses. And that's sort of what's shown here. the pulsars pulses. But then, since you can reprocess data, that actually I find quite nice. You can do both things at the same time. So what they've done here, the pulsar group in our transients KSP, they have measured, phased up the core to give you the many pulses from a pulsar, and at the same time use the data to do the imaging. So this is an image from the cross correlation, and this is sort of the pulses from the phasing of the array. So you can do two things at once. So that's very nice. Yes.
For the crab, can you image it in the giant pulses alone?
Yes, that's all we'll show you later, and we've done that with the TVPs. That's actually the upshot I'm trying to get to. This is actually early days, and this with 5 pulsars. Now the data quality is much better. This was actually when the stations were not really well calibrated, so the pulses are crappy actually. But what they've done here is look at 5 different directions at once, which are fairly widely separated on the sky. So they timed 5 different pulsars with the same array, and that shows the power of phased arrays that you can use. This. And now pulsar science is coming, it's going very strongly right now. They've done 90 pulsars, looked at the evolution of the pulse as a function of frequency, because you see you have so much relatively broad frequency range. You see the pulse changing as a function of frequency and time. And then, exactly what you were suggesting, the giant, the crab pulsar, once in a while it makes very powerful pulses. And we've wrote a real-time medium dispersion, and so pulses arrive at different frequencies at different times in a very well-defined manner. It goes with lambda squared, essentially. So here we have 4 pulses at 4, and then actually we triggered the buffer boards, and we're reading them out. And that is all sky. That's an all sky image. So the resolution is poor as 5 degrees or so, because it's just one station which doesn't have any resolution at all. Yeah? So we would have to combine multiple stations to get the high resolution. But nonetheless, it's just proof of principle in this case. So this is 5 milliseconds of data. Yeah? So it's 5 milliseconds. So it's not. Sorry, it's 50 milliseconds of data. You see the galactic plane, Cas A, M87, Crab Nebula, the Sun, and so that's what you get if you average it, and then you sort of zoom in and actually make a movie sort of every 100 microseconds or so, and see where the right. So that's a movie on the crab. This is just no noise flickering. There's a time here, and then bang, suddenly you saw at that location there was a flare, right? And so the idea is really you look in sort of a large beam. You see a flare, you don't know where it came from, then you go back to the buffer boards, and it tells you right there at the crab was a flare. Of course, in this case we knew, right? It wasn't a surprise because we were expecting it to do this, but hopefully find things which you didn't expect. That's the whole idea of this kind of research.
But okay, you said there was nanosecond time structure in these giant pulses.
At these low frequencies, you have dispersion and scattering, and the scattering you cannot. But yes, you would have the resolution to see 10 nanosecond pulses. It's essentially 100 megahertz bandwidth to get 10 nanosecond resolution. So that's what you can do. And actually do it for the cosmic rays. Which is kind of the skip the order here, which is not very smart. Sort of a pulse coming from the sky, but you can also look for these ultra high energy cosmic rays hitting the Earth's atmosphere. And so, why am I showing this here? I shouldn't be doing this. I'll skip a few things and then I'll go back to it later. To test this kind of idea and to sort of prototype this use of the buffer boards, we actually put some radio antennas into a detector array that was built in Karlsruhe to detect ultra high energy cosmic rays. So you see this particle and then getting the radio emission that was associated with it. In Zenith, then you see here a source blinking. It blinks because the movie repeats. It's not a pulsar, it's sort of one cosmic ray. And we know that exactly at that time, from the particle detectors, a cosmic ray had hit the Earth's atmosphere from that direction. So that is lobes in time and in space. It's the main lobe, but also side lobes. We haven't done cleaning. And you also can do 3D, because we can do sort of look for curved wavefronts. We don't have to look for plane waves, we can look for curved things. And so that's how we can distinguish something that comes from near Earth something which is outside. I think that is the key, perhaps, to also some of the SETI things we want to do, because that's how we can distinguish, man-made stuff from kilometers. And then, you see that we make actually an image of the entire volume again, and then you see that sort of here at 4 kilometers height, the radio emission has peaked. Your beam, has a tail in this direction. Because so that is very research. I'll just briefly mention that. We've shown that the radio emission, for example, this is energy here. This is the radio pulse. That's the energy of the radio pulse. Let's skip that part, and I'll go back. Actually, sorry, it's a bit unorganized because I want to then show what we're doing with LOFAR. Now in LOFAR, we actually, and so this is again a display from one LOFAR state. Go back. Right. That was post-processing. So and that's actually from could be windmills or whatever, or airplanes. Some airplanes does it. One radio pulse, and you see now these are all side lobes. And you sort of bang. You see here was the pulse from the airplane, which we sort of localized. It's sort of almost 80 degrees. You have the source there, or sky. That we've seen in our interferometry data, and people have struck the track of the airplane over half an hour. So that's half an hour. I actually went back, and they also found out that they are known to produce interference because they have sort of 40 Honeywell. Next time you fly over Europe, switch off your iPhones because then we want to track you. So that's that's because I changed here the order of direction. Now. This cosmic ray stuff, cosmic rays which are rather rare, right? And so what counts we array are 3,000 square kilometers. And the idea is, okay, what's the biggest detector we can use? The biggest detector we can use is the moon, because that has 9 million square kilometers of sort of empty space. And luckily, we are going back to the moon. Well, so since we are not going back to the moon, we at least can watch the moon from a distance, and that's exactly what we do. And we've done that as an experiment, verified in a laboratory experiment. And then you receive that with your telescope on the ground, which was not surprising. But at least this is sort of here a plot of neutrinos lower at this part below this. So that's what we reach. So it's a very rough estimate. There's always one guy you can rule out. It's not a very sensible one, if you ask me.
In the previous slide, you had the 100 megahertz waves.
Look a few, say, kilometer or a few hundreds meters deep into the moon. Cosmic rays will hit on the surface. They have a slightly different, so that's you have to do slightly different calculations, and that's what we've done in the next slide, calculating that same upper limit into cosmic ray flux. This is the measurements right now done from the ground at up to 10 to the 20 electron volts from Auger. This is Westerbork, so far away. But interestingly, LOFAR actually gets very close, and this spectrum we don't know. There's a little change in spectral index. And then now let's do the interesting stuff. Can we use that for SETI? Well, there are some thoughts I had. Intelligent life is probably rare. So as you know, so there are a few thoughts I had. One is, an EG signal. I think that's where LOFAR really has an advantage. It can do for you a large field of view thing. And if it's not targeted, it's very likely going to be transient. Good, follow these things up and verify there was something. Because usually you have a signal, you have a wow signal or a wow through signal, and you don't know what it is. Right? If you have it in the buffer wards, you can later verify the sort of a transmitting power size of the antenna, sort of baseline of your transmitting antenna. Be only seeing out to 10 parsec. And you would have, and how well it actually goes through the interstellar medium. That's one thing one needs to think about. And it would be sort of narrow band, some tens of hertz at 120 megahertz. You would see it out to 10 kiloparsec within 1 second. So that's the kind of thing actually you could, in principle, see, either as a transient signal or as a constant transmission. And in fact, since you can do it in 1 second, this is the time scale of our buffer boards. The idea here is, okay, what you at least can do, you can exclude at least that someone is intentionally transmitting at us. I'm now used to upper limits. 10 years ago I said I'm never going to do upper limits. Now I said, at least I can do an upper limit now. If I use sort of a 1 second, and what I didn't say, this is actually incoherent dipole beam. So this is just incoherently adding all individual dipoles together. So it's not just beamforming, it's just adding up the spectra from individual dipoles. Where the signal to noise grows with the square root of the number of antennas, not linearly with the number of antennas. That's the difference between coherent and incoherent beamforming. Something you could do, and then you could later go there and say, done that, look at all the lines, and then later in offline actually find where those lines were coming from. Right? So I can say this came from the horizon, this came from the sky. And so at least that gives you some quantitative measure. And my argument would be, if anyone wants to talk to us, and they're sort of on this time scale of a galactic distance in kiloparsec, then they better use low frequencies, because that's the first technology where you can do this. Right? That's the first low frequency all sky survey you can do in 1 second with, actually everyone can do that. Everything else is, as you know, is very time consuming. When you've looked at sort of the 1.4 gigahertz lines and the frequencies at the nearby stars. So if you have to look further, if you really have to do an all sky survey, not just target individual stars, then you better go to low frequencies where you have this large field of view. That would be the argument that I would make. And if you don't find anything, then okay, then probably nobody is smart enough to really want to target us. So that's a statement. So that's I'll explain all of this already in sort of in brief words. So what can we do? I mean, that's one idea. I mean, of course, you can still do conventional safety searches and targeted observations. That actually has already been and so that might be something you want to put it on stars, or you may want to actually just do a blind survey covering a large field of view with those, because those 50 tidal ray beams, give you already quite a large fraction on the sky. So that would be also an interesting thing to do. So just to show you, this is a TBB spectrum with 10 Hz resolution. So I can run this on my MacBook, add all the antennas up. So the processing actually for this OSAS, in principle, is the frequency FFTs and so forth. You can do this in a couple of days to process this 1 second all sky survey. Add up all antennas. I mean, you don't have a waterfall spectrum, right? Because you only have 1 second. You don't see a dynamic spectrum as a function of time. So you only see where there are lines. These are obviously shortwave radio lines. What you then can do is you can pick out where these lines are.
Why do you say obviously?
Sorry, what did I say? Obviously?
Why are they obviously shortwave radio lines?
Because they're in the frequency range. And that's why the chance is the highest that this is there. So if I'll test it. But the first thing I'll do, I will not go to the 12 megahertz regime where you have lots of lines, where it's a lot of computation intense. If you go to the frequency range from 30 to 80 megahertz where there are very few lines, then you can make already a first, could make a first paper on this on 50 megahertz just, and then you can do a second step, the hard stuff, right? So that's, I'm very opportunistic in this respect. This is one problem is how do you do phased arrays. That's I don't want to. That's something I need to say is phased arrays have a problem when you go to continuous waves. Because a continuous wave is sort of if you shift a continuous wave on one this is from this airplane pulse. Here you see the pulse. This is frequency. This is time. He took one of those frequencies, I think somewhere here in the regimes, and tried to map it. And what you see right now, there are actually at least 3 different possibilities where it could come from. Now we have not really explored all the side lobes. I think once you understand your side lobes, you can actually tell which one is which. But at the moment, I would not dare to say it's this one, or this one. I suspect it's one of those, and this is a side lobe. But my students think this is it, and these are the side lobes.
Do you have any idea how long those side lobes are stable, or how they will change in time?
Yeah, they definitely. Yeah, that's absolutely true. They would of course change with frequency, but we only have one. That's why if you have sort of phase changes in there, that would help. But then if you look as a function of time, it definitely would also change on this. So seeing it twice So doing the same thing twice or 3 times would help. But also, this is one station. We have 27 or 40 stations in the future, actually separated over the entire continent. And most RFI, even that airline RFI, I mean, we saw it 30 minutes, but it would be difficult to see it in Poland and UK at the same time. At least there's another way of excluding this. And again, by getting directions from Poland and UK, you can actually triangulate. And if you have high signal to noise, you should be able to distinguish something actually out to a geostationary orbit. And Philippe, they looked at sort of, had a targeted. This is just 1 star, so it's not yet on any.
So it's Alan Penny that you're
Yes, yeah. So, probably because it has lots of possibilities to work with, a lot of things to do. But I think it has the potential for some significant LOFAR, and perhaps some of the top people in LOFAR are actually interested in this. I mean, as a sort of side project, you can't do it full time. Not the entire community wants to do it, but it's not. And time was granted actually. There's some official time granted to do it. And what's for me important is there's nice synergy with the transients and cosmic ray KSP. The same techniques, the same procedures we use, we can actually use also for SETI search. I mean, the SETI is sort of a little extra step in certain areas. Some things, and if you want to really do a full search of a dynamic spectrum or waterfall diagram, we don't have that. We're not going to do this, so you would have to do that, right? So, so some of the basic data products I think should be there, and also with the TBBs, you could also think of distributing that to the community or whatever if other people want to look at it. That's certainly something I would be using. Yeah, and then the buffering technique I think is a new aspect of it. Large field of view, large frequency range, duty cycles, and most importantly, test whether the signal is terrestrial. Yeah, I said that already. So yeah, I think consider low radio frequencies for it. I think that's something to do. A telescope is there. A lot of a lot of things you can play with. That's okay. Thanks.
So you're pointing to the offline processing needing more capability or horsepower than you have with that 100-node offline cluster?
Well, in principle, this 100-node one would probably be sufficient if I had it on my own. So, at this moment, I would even say it's not just limiting in computation power, it's just limiting in manpower, just putting this to work and doing all this offline processing. Actually, a lot of these things, I actually have done a lot more than I was able to show because I couldn't make images in the lack of time in recent weeks. A lot of the basic things are in place. We can make images, I can make 1 hertz spectrum, I can localize the pulses, so I could run in principle an entire SAT pipeline in the sense that I can localize things in the TBB data. I could not at this very moment, search a dynamic spectrum for an interesting SAT signal. That's software I don't have, and I'm not going to write it on short time scale. The other one I have. And what needs to be put together. You need to have someone really working on it and making it work.
Can I just ask? I'm sure that I got this wrong, but because of the buffering capability of this thing, does this give you the possibility? Say you're looking at given wavelength range, and over the course of a second there is a very short pulse, right. 10 nanoseconds or more pulse. Okay, that allows you then to go back, do the correlation, find out where on the sky that pulse is. Did I get that right?
Yes.
Because that seems, Jill's heard me and Doug has heard me for 5 years, hammer this stupid point that because they're not within 70 light years, they're probably not sending us a relentless signal. They're sending us an intermittent signal to say this part of the sky is interesting and you should pay attention to it. But that involves looking for transient sources. That's very hard to do with the kind of instruments we've been using because you're not looking at the entire sky. So this would allow you to do that.
Absolutely, that's exactly what we want to do because we want to do it for the neutrinos, right? Then we have a very distinct area we want to look for, so we place multiple beams on it, and then we want to see, okay, pulse, dump, and verify it came from there. And the second one is to look for crab-like pulses. There may be other pulsar-like things out there, and they have very short pulses which will be dispersed. We look for dispersed pulses. We'll dump the buffer boards and then find out where they are. And the interesting aspect is, what you can do is you can do the imaging, and then you can make actually incoherent beam of all the stations. Yeah, you sum up the beam from all stations, and then you get a very large, a couple of square degrees beam on the sky, and then you can, in principle, run all the time parallel to imaging observations, because it costs almost nothing. Then you run actually on the offline class, so you can run this pulsar.
There's no transform.
And the idea is that we do this anyway, because we want to find those pulsar-like things.
Right.
Right? And so you just have to do a little extra step to say, okay, that's an upper limit on a SATI signal or whatever. I mean, maybe it looks slightly different, but actually you get them. You get this information. And yeah, and then you can go back to the TBBs if you dump fast enough and verify actually it came from there. And exclude whether it was terrestrial or not.
That would be very interesting. That would be very interesting. Particularly since it can be, because you don't know what the repeat time might be. It might be, exactly. An hour, it might be a day, it might be a year. Exactly. You have no idea. But this instrument allows you to essentially look for it all the time.
Well, no.
Yes and no. The TBB, you have sort of 1 second, then you have to dump it, and that can take a quarter of an hour or so.
That's right, but if it repeats only once every 6 weeks, that's okay, right?
No.
Well, no. Because with the TBBs we have all sky, but if we have one signal on the sky which repeats once every 6 weeks, it has to come within this incoherent beam then, within the few square degrees. So then we have to look we have to have 10,000 pointings or so, thereabouts. So once every 6 weeks would not be good. We still cannot do all sky with that sensitivity. Yeah. Right?
Yeah, it's still it's the duty cycle of
duty
how many, that 1 second on the sky that you have the data in the buffer, but then it takes much longer than that to read it out to something.
Yes.
And you have no sensitivity while you're doing that.
Yes, and so you would have to trigger on it. If you can trigger on it, then that's fine. But the trigger you have to get received probably within a beam. And that again selects only a part of the sky. But that again is very large. I mean, it could be a few square degrees. If you can restrict yourself to a narrow bandwidth, then you can have actually not just one beam, you can actually have 50 beams with a fraction of the bandwidth and thereby cover a much larger area on the sky. You can trade beam bandwidth for a number of beams. You can have up to 200 beams on the sky.
And you can trade bandwidth if it's a pulse that will be broad enough.
So that's a very narrow pulse.
That you
then yeah, because it's going to be dispersed anyway, you could afford this. But then it has to be, of course, fairly strong. You don't have 100 megahertz bandwidth, you have to have it then within
but this is virgin territory.
200 kilohertz, yes, the pulse you have to see. Absolutely, yes, sure. Yeah. And again, we don't know what's the best strategy. Also, we don't know what's the best strategy for the pulsar search. You just have to try.
What stops you doing this at 1.4 gigahertz?
The receivers, for one thing, aren't cheap anymore, right? He's got coat hangers, so it can have lots of detectors. When you get up to 1.4, you're shaping it with an antenna, a dish, and in fact, so we don't have 50 beams on the sky. We only have 3 beams. What's limiting us is the dump time of the correlator, which is not very fast. It's 10 milliseconds. Spectral resolution in the correlator. There are variants of this that we're trying on the Allen telescope already, but there's a lot to be said for a dipole that sees everything above the horizon.
I should make one other restriction, that is, this is for low-band antennas. For the high-band antennas, we have 16 dipoles which are analog beam-formed. And so then you have 2,000 square degrees on the sky. So if you want to do it from 120 to 200 megahertz, then you have, that's important to note, you don't have all sky. Since you always get things in from the side lobe, you could still sort of localize things that way, because they still arrive at different stations differently. But the full sensitivity you only have in the main beam of those tiles. But still fairly large. I mean, it's 1/16. I mean, 16 dipoles, right? It's 1/16 of the sky. So you could make 16 pointings with it. So that's and you could repeat this 1 second. If it's you could repeat it every day or every hour.
Yeah.
could be lucky.
Is
It
there-
finds this one needle, right? So that's great.
So is there some argument that you can make that repeating this every, I have no idea what the cadence is for your other observing kinds of things are, but repeating this every minute, every 10 minutes, every hour, some kind of cadence helps you calibrate the array so that it's something that you would put into routine operation?
Some of that we'll do, I think, anyway, because you want to do this transit hunting anyway. So we'll trigger on something, and then, I hope that every hour we're going to make a dump. Right, not right now, because that, this requires operational pipeline. We're not there yet. But my hope that at least every hour we're going to have such dumps, every half hour. We're also going to have the cosmic ray dumps, which are much shorter. There will be millisecond timescale dumps, but these other ones you can have more often. There's no limitation to it. It's just because they're being used for the transient searches. That's what you want, or they will be used for the cosmic rays. These will be then shorter ones. They run mainly in the LBA frequency range, and this will be only on probably a quarter of the time, I suspect. So yeah, so a significant fraction of the time this could run all the time. But then, this is 1 second is a terabyte of data, or multi-terabyte. You're quickly a petabyte of information.
Mm-hmm.
Yeah, I'm used to this, but...
No, I mean, we only get 100 terabytes a day of
Right.
raw data from the Allen telescope, right?
Yeah.
So this will generate a lot more if you tried to do all the raw data. It's a really nice instrument.
Yeah.
You were saying about the stellar and planetary flares.
Yes.
Do you really talk much about how can you...
Essentially the same way. It's essentially the same way. You could either target them, or you actually within the same, with the same method, you would have to write the right trigger algorithm to look for less dispersed pulses, because they're probably, but that's what we do anyway. We want to look for low dispersion pulses, because the first thing we want to do is sort of within 100 parsecs see if there's any dead pulsar, which once in a while pulses. And if that dead pulsar is actually a brown dwarf, hey, I'm not going to complain. Right, so that's yeah. The pulses may be longer, right? They may not be sort of millisecond, and maybe not the microsecond, maybe milliseconds or longer. That's the only difference I see.
Yeah, it's interesting that with optical SETI, the one thing that we haven't found is a natural background of a nanosecond duration,
Yeah.
but we have it in the radio.
The pulsars, yes. That's good in the sense because it gives you guaranteed signs. And we have those brown dwarfs and possibly exoplanets, but certainly brown dwarfs will do it. You'll find the flare stars. So those will you find, I think, for sure. And so it's not, that's why it's safe to do it, right? It's not just an upper limit. It will give you some guaranteed signs. And at the same time, you can turn it into a city experiment without much cheating, actually. So it's quite reasonable to do. Okay. So as I told to you, and this is open. Lobos telescope is not a closed thing, so people interested, will.
The Vinglo?
Sorry?
Where is it headquartered? Vinglo?
The telescope?
You're in Nijmegen.
I'm in Nijmegen, yeah. So we're mainly doing this kind of stuff. The TVBs is our territory. The telescope itself is in Exlo. It's sort of southeast of towards Emmen, if you remember.
And actually, you asked about doing it at 1.4 gigahertz. When we did SETI 2020, we looked at the omnidirectional sky survey for transients. And so we aggregated up. Our detectors weren't dipoles, they were equiangular spirals, small things. And to get enough collecting area and to do the high spectral resolution, we calculated that you'd need 10 to the 21 floating point operations per second. So I'm interested that you're getting, with the dipoles, you're able to get.
The trick here is that you select. So you want to do the imaging only at select frequencies. So you make first a spectrum. Doing the spectrum is, I think it's a minute per dipole.
Okay, so that's
2,000 minutes on a MacBook. So you can have multiple nodes, of course. You can do the spectra, and then you look at the various frequencies, and then making the image actually even. This is done in hours or minutes.
Yeah.
So.
Yeah, because we were always looking at what you would need to do it in real time.
Yeah. Okay.
Carry on.